Okay, good morning, everybody. How was your weekend? Hope you have a nice time. So I welcome you to the lecture for this week. So as usual, we go to continue from where we stopped the last week. In the last week, we started the notion of Fourier integrals and Fourier transform. So what we are going to do today is a follow-up to what we have done, what we did last week. So this will be talking about the Fourier sine and Fourier cosine integral. As well, the Fourier series and Fourier sine series. So today we want to talk about Fourier sine and Fourier cosine integrals. So if your function f of s is an even function, then by symmetry, the Fourier transform of f of x, which is capital F of k, is this by definition that I told you last week. Because f of f is an even function, so you can have it as 2 over pi into integral from 0 to infinity f of s cos ks ds on the condition that your function f of s is an even function. So if f of s is an odd function, then the Fourier transform of f of x, if f of s is odd, by definition is this, and because f of x is odd, you're going to get this, because this is just twice from 0 to infinity of this, so we get 5.8. Now, the fk 5.7 is an even function. The Fourier transform if that of 5.7 is an even function, since it is a function of k and cos k is even. So thus, the small f of s is also, if f of s is an even function, then the Fourier transform is also an even function. The same thing happened with what you have in 5.8. If f of s is an odd function, then the Fourier transform is an odd function. You must take note of that. Okay. So by symmetry, if f is even, if f of s is an even function, then the Fourier integral by definition is given as this by definition. But we can write e raised to power ik as cos ks plus I sin ks. So you just plug e raised to power ikx as cos ks plus I sin kx. So when you multiply by capital F of x, so you're going to get this, the next integral. So f of k, because we assume that f is even, if f is even, capital F is even, cos is even, the product of even function is even. So this is an even function. So capital F is even, sine is odd, so the product is odd. So since the product is odd, this integral will be equal to 0, and this is not 0. So whenever your function, f of x, is an even function, then the Fourier integral will be twice of integral from 0 to infinity, the Fourier transform of that function times cos x ds. So you must note this. Okay? So the Fourier cosine transform of f of x is denoted by capital FC. So this is just denote cosine. So just to differentiate sine from cosine, So the Fourier cosine transform without C is just the Fourier transform of f of x. But this C is just to tell you that you are finding the Fourier cosine. The Fourier cosine transform of f of x is given as 5.9. So f of c means the Fourier cosine. The C stands for cosine. The Fourier cosine of small f of x is just 2 over pi, integral from 0 to infinity, f of s cos ks ds 5.9. So if that is the case, then the Fourier integral theorem yields. So if you want to find the Fourier integral for a function that is cos, that is all even, so you just replace your capital F of k with the Fourier cosine transform of it. So this is it. So this is what you're going to have. Okay. So the same way, the Fourier sine transform. So for sine, you just use what's it called it? X for to denote cosine sine. So the Fourier sine transform of small f of x is given as capital F subscript k of s, and this is given as 5.11. So this is just 2 over pi, integral from 0 to infinity, f of x sine kx dx. So the difference between the difference between the Fourier cosine transform 5.9 and the Fourier sine transform 5.11. So it then follows that the Fourier sine integral of the function f of s is this. So you just replace your f of the Fourier transform with the Fourier cosine transform. You are done. Okay. Okay, let's find this example. Look at this example. So find F. What is this F? This F stands for Fourier transform. This capital F stands for Fourier transform. This stands for Fourier cosine transform. Why this capital F stands for Fourier sine transform? Fourier transform, Fourier cosine transform, Fourier sine transform. So we want to find the Fourier transform, Fourier cosine transform, Fourier sine transform of this function f of x. 1 minus x squared for modulus of x less or equals to 1 and is 0 elsewhere. Okay? The way we define f of x is 1 minus x squared if modulus of x is less or equals to 1. So modulus of x less or equals to 1 implies minus 1 less or equals to x, x less or equals to 1. That is what it means. That is what it means. And it's 0 elsewhere. So this function is an even function in x. Because it's an even function in x, then our f of k by definition, this is f of k by definition. The Fourier transform by definition is this. Because our function is even, then we are going to have twice from integral from 0 to 1 minus x squared cos kx dx times 1 over 2 pi. Okay? So between 0 and 1, f of x is 1 minus x squared. So put f of x 1 minus x squared and cos kx dx. Here you are going to use integration by part twice, which I've repeatedly told you what to do. So you are going to use integration by part twice to evaluate this integral. So after integration by part twice, so you're going to get a capital F of k as capital F of k will give you 2 into sine k minus k cos k all over pi k cube. So after you use integration by part twice on that integral, so this is what we're going to get now. So this is your Fourier transform, Fourier cosine transform of that function. So since your f of s is even, f of k is even. Is that okay? F of s is even, means f of k is even. Then the Fourier, the Fourier integral of f of that function will be equals to integral from 0 to infinity, minus infinity to infinity f of k raised to the power I kx dx. So what do? Just plug your f of k. This is your f of k. So this is your f of k. Just plug this f of k and replace it here. So just carry your f, just take your f of k that you already obtained earlier and just plug it here into the power I kx dx. Okay. This is this by definition equals to 1 minus x squared if modulus of x is equals to 1 and it's equals to 0 s squared. Okay, let's try to find the Fourier cosine transform. For Fourier cosine transform by definition is the one with capital F subscript. I've told you the seed is to tell you that I'm finding the cosine part. The Fourier cosine transform is 2 over pi 0 to infinity f of x cos kx dx. So between 0 and infinity, f of x is only defined between 0 and 1 and is 0 elsewhere. So f of x is only defined between 0 and 1, that's 1 minus x squared. S squared is 0. So we're integrating between 0 and 1 minus x squared cos kx dx. Then you also have to use integration by part twice. You must integrate this one by part 2 times. So when you do that twice, this is what you're going to get. Integration by part twice. So it follows that your Fourier integral of f of x is 0 to infinity, integral from 0 to infinity, Fourier cosine transform of f cos kx dx. So this is your fc of k. So just plug this, then you put it here, times cos kx. So which is equals to 1 minus x squared if modulus of x is not equals to 1 and is 0 otherwise. So now I've told you how to find the Fourier transform and the Fourier cosine transform. Okay. For Fourier sine transform, so this is our fx of k, the Fourier sine transform. That's 2 over pi, taken from 0 to infinity, f of x and kx dx. So put f of x is 1 minus x squared between 0 and 1. This is 1 minus x squared and kx. Use integration by part twice. Integration by part twice, then you go to get this. You're going to get this. You must figure this out. Just integrate by part 2 times, which I believe you know how to do by now. So since the Fourier sine transform is odd, since f of s is odd, so it then follows that your Fourier transform and the Fourier integral of f of x is this. So what have you done? Just replace you come up here. You just replace, this is your capital Fourier cosine transform. This is your Fourier cosine transform. So you plug it in, sine kx dx. So this is what it is by derivation. So I put some notes here that there's a jump on discontinuity at s equals to 0. And the integral converges to the average of the limit from the left, which I've told over time, which is -1, and the limit from the right, which is 1. So what do? -1 plus 1, that is 0/2. So it converges to 0 at s equals to 0. So the limit converges to 0. So 0 at s equals to 0. Okay. Now find the Fourier sine transform of f of s equals to e to the power minus cx, where we assume that our c is greater than 0. So find the Fourier sine transform of f of x equals to e raised to the power minus cs, where c is greater than 0. So by definition, our Fourier sine transform of f of x by definition is this. So plug in your f of x, which is e to the power of minus cx sine kx. Okay. Now what you must know is that you can always split this e raised to the power I. You can always split e raised to the power I kx as cos kx plus I sine kx. So we need the part with sine. The part with sine is just the imaginary part of this integral. So this integral is just the imaginary, because when you split e to the power I kx, we are going to have cos kx plus I sine kx, and you're going to multiply with this. But we don't need the whole of the integral. We only need the one with sine, the part with sine. So the part with sine is just the imaginary part of this. So we only take the imaginary part. So we integrate this. After integrating this, we take the imaginary part of it. Okay, so when you go down, here you only apply your law of indices. The base is E, so you add the part together, so you get this. So you integrate. When you integrate, you have this. Okay. So after putting the limit of integration, you get 1 over the imaginary part of 1 over c minus ik. You already multiplied by 2 pi. So what are we doing here? Here we are only rationalizing. We're rationalizing the denominator. So this over this is 1. And when you multiply, so this is c squared plus k squared. So we split this into 2. So this is going to be c over the denominator plus ik over the denominator. But we want the imaginary part. The imaginary part is the part with the I. So this is the imaginary part. Imaginary part is k all over c plus k squared. K over c plus k squared. C over the imaginary part is k over c plus k squared. So we take it out, which is this. We multiply by 2 pi. Okay. So it then follows that the Fourier integral of the function is just 2 over pi. This is our Fourier transform, Fourier sine transform, which is capital F S at K. So you plug it here, then you go. So it converges to e to power minus cs if s is greater than 0. Converges to 0 as s equals to 0, and minus e to power c if s is less than 0. Okay. Okay. So let me briefly talk about Laplace transform. I have some charts, I have some chart and inverter information for you at the end of the class. So I need to talk about the remaining part of our test. I'll put an information on Moodle for you this morning, but I'll give you the update after the lecture this morning. So using Laplace transform. In some cases where the calculus of residue phase, we may resort to Laplace transform to find a Fourier transform. So let me briefly recall what Laplace transform is all about. So if you have a function f of t, for t greater or equal to 0, the Laplace transform of f of t is this. So this S stands for Laplace. So this is the Laplace transform of f of t. So this denotes the Laplace transform of f of t. So by definition, if you are given a function f of t, where t is greater or equal to 0, the Laplace transform of f of t, by definition, this is definition, is integral from 0 to infinity, e to the power minus xt, f of t dt. So this is a function of x. So the Laplace transform of f of t is a function of x. So it's what we call the capital F of x. We call it is capital F of x, which is a function of x. The Laplace transform of f of t is given by this integral, and it's a function of x. So I call it definition 1.5.3. By definition, you need to note this. If you want to find the Laplace transform of e to the power at, where a is a constant in R, f of t. So whenever you want to find the Laplace transform of e to the power at f of t, is just the f of x minus a. So what do? This is f of x. We just replace x here with x minus a. So this x becomes s minus a. S minus a. So this relationship is very, very important. This is very, very important, which you must know. This relationship, Idoma figure 1, is very, very important. Okay, let's look at this example. Find the Fourier sine transform of f of x, which is equal to e to the power minus x over x. Now, the Fourier sine transform, this is the Fourier sine transform. So x is there, Fourier sine transform, that's 2 over pi, my definition. Integral from 0 to infinity, f of x and ks dx. So plug in your f of x. So f of x is e to the power minus x over x. This is our f of x, multiplied by sine x dx. Okay? Now, what you have here is just the Laplace transform of sine kt over t. This is just the Laplace transform of sine kt over t. When you go to 5.13, look at 5.13, where we define the Laplace transform. This is Laplace transform. So if you go to 5.13 and you replace your x with t and this other x with 1. So this guy here, this integral here, is just the Laplace transform of sine kt all over t. Then by definition, I don't want to bother you with this. It's another topic on its own. I'm not going to lay more emphasis on Laplace transform. So the Laplace transform of sine kt over t is just r cot t, r cot s over k. So note it, this is a note for you. So the Laplace transform of sine kt over t is just r cot s over k. So, but you must put your x is 1, and you must put your this is as t. So this is going to give you r cot 1 over k. So this is Laplace transform of sine kt over t. So eventually, you are going to get 2 over pi at tan k, because cot at 1 over k is just the same thing as at tan k. So this is what you have at the Laplace transform. So I'm not going to bother you much about you finding the Laplace transform of some standard function. So it's out of the scope of what I'm teaching you in Maths 354. But I also want to tell you that sometimes the residue theory may fail. If the residue theory fails, then you can resort to using the Laplace transform definition that I have in 5.13. Okay, so that is basically what we have this week. So I don't have much this week. Let me look at the chart. I have some chart here. Let me look at what this chart is saying. Good day, Prof. What is the content of test 1 on Friday? Okay, so I will say for now, just take your book and read from where you stop. You know where we stop our last assessment. So what I've examined you in the past, I'm not going to examine. So from where we stop for the last assessment, so start reading from there. And what I'm teaching you this week, I will not examine it. Is that okay? So please repeat when to consider imaginary and the real part. Okay, I will repeat that. Please repeat when to consider imaginary and the real part when you meet the residue phase. Do we mean that we get an undefined function when you see residue from the other lemma? Okay, now let me go back to the question. Now you come back to the question you tried to ask me. Okay, let's go back a bit. Okay, let me go back a bit. Understand what you are trying to ask me. Let me see where I have the question and quickly answer that. Okay. Okay. Now, we want to integrate from 0 to infinity e to the power minus ax sine kx dx. Is that okay? So, I want to integrate this, but you must recall that e to the power ikx is equals to cos kx plus I sine kx. So this guy here is just the same thing as cos kx plus I sine kx. So when you multiply with e to the power minus c, so you are going to get e to the power minus c, e to the power minus cs cos kx plus I e to the power minus cs sine kx. So now, when you relate with what you have here, we don't need the whole of this integral. We only need the part that contains sine. The part that contains sine will be e to the power minus cs sine ks, and that is the imaginary part of this integral. Is the imaginary part of this integral. So that means when you integrate this integral, the value of the imaginary part of this integral is just the same thing as this. So that means we take the real part off because we don't need the real part. But if you are to evaluate integral from 0 to infinity e to the power minus ax cos kx dx. If you want to integrate the one that involves cos kx dx, that means you take the real part. You take the real part of this integral. The one that involves sine, take the imaginary part. The one that involves cos, take the real part. So that means you record that after the integration, we got, this is what we got after integrating. Okay, so this is what we got after integrating. This is the value of the integral that involves e to the power ikx. So assuming that our integral is the one that involves cos, so we only take this part. This is the real part. We take the real part. So instead of having k over c squared plus k squared, we just have c all over c squared plus k squared if our integrator involves cos. So this is the real part and this is the imaginary part. So that is basically what we need to do. On the issue of Jordan's lemma, there are conditions for using lemma integral, Jordan's lemma and residue integrals. If the conditions are not met, so we said that means you cannot use Jordan's lemma and the residue theory. So at that point, we say the condition of Jordan's lemma and residue theory fails. At that point, you can then come and use your standard definition of what's it called now? Fourier transform, which is 5.13. Is that okay? So that is basically what I mean here. So let me see if there's more other chat on my to respond to. So the weight of the test, just leave that for me for now. So what I want to tell you for now is that I gave you an assignment last week. Please try to submit before Friday. I'm going to give you another assignment by this Friday. I gave you an assignment last Friday. Make sure you submit the assignment latest by this Friday. After Friday, you cannot submit again. The system will not allow you to submit online. And anything you send to my email, I will not accept from you. Because that's why I gave you a full week to work on this. A full week to work on a problem that I can solve within a day. I gave you the full week. So don't come and tell me excuse that, oh, my internet failed. I won't listen to any excuse. You must try to adhere to the instructions that I put in the assignment. This Friday, I am going to give you another assignment for 1 week. Is that okay? This Friday, I'll give you another assignment that will start from Friday and the due date will be next week Friday. I will do that. Okay? So for your test, you are going to have a standard test by this Friday. And another test the last Friday of the month. So I put the time for 5 p.m. because some of you are complaining that you don't want to have your test early in the morning. So because of that, I decided to put the test by 5 p.m., which I believe will be fine for everybody. So the test is as usual. I'm going to put the question online, but I will time you. After the test will be for 1 hour. After 1 hour, if you don't submit online, anything you send by email will not be accepted. You must ensure that you are able to submit online before you are able to submit your solution online before the expiration of time. So anything you send to my email, I'm not going to mark. I'm not going to mark. So I'll give you enough time. I'll make sure that the question that I will give you will not be more than 40 minutes at most. Then you can spend the remaining 20 minutes to scan and to upload. So I'm going to be considerate when I'm giving you time. So I know you have a lot of limitation over there, scanning and otherwise. So I will try as much as possible to give you sufficient time so that you have time to scan and to upload before the 1 hour. So that's what I want to say for now. So I'll think about it between now and Wednesday. I will post on module area to concentrate on before Wednesday or Thursday. I'm going to tell you the area that we are going to concentrate on for the test. So that's what I can say for now. Okay, I will tell you the area to concentrate on the test. But what I can say for now is that what I taught you this week, don't concentrate on that. Don't concentrate on what I taught you this week. For now, concentrate on where we stop our last assessment to what we did last week. That's what I would say for now. Where we stop our last assessment to what we did last week. Concentrate on that for now. If there's any little adjustment before Wednesday or close by Wednesday, I'm going to send a module to you for you to help you to prepare for the test. Okay, thank you very much. I'll put the thought for this week is already on Moodle. Try to work on it on your own and expect my assignment on Friday, which is going to be due. You are going to submit in the next 1 week, and also expect a test by 5 p.m. on Friday. Thank you very much. Do enjoy the rest of the day.